Yeah.
So, thank you for coming. This time I hope we will prove what was intended. And so I will start with a recap of what we did Thursday. So I'll be very synthetic. Please interrupt if you want more details. So the style of this recap, this is like a page and a half, should take us like 20 to 30 minutes. It's really just the bullet points. So recap. The left self-distributive law is the law A star B star C equals A star B star A star C. And I also use LB as an abbreviation for left distributive. This operation is not associative, so you have to distinguish between left powers and right powers. So, for example, something like this is a left power, and so an plus 1 is an star A, and the right powers are you start associating from the right, and you have this notation A star N. Now a Laver table is an algebra of cardinality n. So it's left distributive. It has one generator, and it has a left identity. So it has an element that acts as an identity. So the only property that we need about Laver tables has to do with their multiplication tables, which is the rows are periodic. The periods are powers of 2, and they increase very slowly. They increase slowly with n. And then we have the Laver-Steele theorem. Laver-Steele, that says that the periods of the rows of Laver tables tend to infinity, then to infinity under the assumption of the large cardinal axiom, I3. So this is what I wanted to remind people what we did on the first section. So I'll now go remind people what we did in the second section, which had to do with but set theory, and I will be equally succinct, I hope, please. So ordinals, I will not say what they are. I will just say that they are generalizations of natural numbers. We can see natural numbers defined by their as being sets, and they are the set of its, or by definition, the set of its predecessors. And also, I define what the well ordering is. So I won't define it again, but I'll just recall that any well-ordered set is isomorphic to an ordinal with the membership relation. And so we have this, the order type of X equals alpha in this case. But the important thing is that there are no infinite descending sequences of ordinals. So there's nothing like this. So no infinite descending sequences of ordinals. So I have a interesting trivia. Do you know who was the first guy that applied this to functional programming? Sure. First name starts with Alan. The first name is Alan. It was about the typed lambda calculus. So it was unpublished. People discovered this after his death in his papers. So he promised. So there's a paper in 1942. He talks about the forthcoming paper, and in the notes we discovered that he used this. Wow. So then limit ordinals. Another thing you need to know is they have no predecessor. We talk about some like omega plus omega, things of this sort. You don't need to know what they are. Just this, and then the von Neumann hierarchy. Which is simply the universe as this is V-shaped. And the ordinals, they work as a clock that says when sets appear. The ordinals are the clock. So the ordinals are the central thing. And at these limit stages, it's like if you had a mini universe of set theory. Then, well, it's not really important. So if alpha is less than beta, then V alpha belongs to V beta, and also V alpha is contained in V beta. So this hierarchy is really cumulative. So So V omega, so V omega plus omega sees everything that V omega sees. There's this notion of rank that I will skip. It's not important. And if gamma is limit, then as I said, V gamma is like a small universe, and it's closed. It's closed under functions between its elements. Its elements. So if you have a function from x into y, then if x and y are in V gamma, a function from x into y also belongs to V gamma. Finally, the notion of elementary embedding. Elementary embedding, which I will not define, but it's just it says that whenever you have elements whenever you have elements A1, AN in V alpha, then whatever V alpha says about A1 and AN, V beta says about their images, J of A1, J of AN. So in particular, if you have a function in V alpha, its image J of F, and F goes from X into Y. J of X will go from J of X into J of Y. And
so J itself is in what? V
alpha V max of alpha plus 1. J will be V max of alpha beta plus 1. Sorry?
Isn't beta necessarily at least?
Yes, so actually it's going to be beta plus 1. Usually you don't have to go much more. It depends on there's a way of coding pairs, which is goes back to prime, where you don't have to increase the rank. So it's so this is enough.
One question.
Yeah.
So you said whatever V alpha says about V1 to AN.
Yeah.
But like V alpha doesn't have any intrinsic, it's like whatever set theory says about V1 to AN, set theory also says about JN. There's no distinction. Alpha isn't saying anything different with V1.
Mostly not.
Statements are just like logical connectives and belongs to.
Yeah. There are some, for example, suppose alpha is smaller than beta, and there's and the first inaccessible is between alpha and beta. V alpha thinks there's no inaccessible cardinal in the universe, and V beta says there is an inaccessible cardinal. So, but for all of the things that we need, for all of regular math, it's the same. It's as you say. So things are absolute. So function, something is a function. It's really a function. And all of that. So if something is a field, it's a field, it's really a field. So only the more sophisticated stuff are not absolute. And now the formula that we are going to need, that is J of f of x is J of f applied to J of x. So then we have this notion of critical point. So if J was different from the identity, then there was the least ordinal moved. We would call it was called the critical point. Critical point. So critical of J means that J of gamma is bigger than gamma, and J of sigma equals sigma for all sigmas smaller than gamma. It's the first point that it's moved. And so basically, you're at a certain, if you have a set and its rank, if it has appeared before gamma, then it's not going to be moved. So any set, not just ordinals, but it's not going to be important. The critical point is inaccessible. Gamma is inaccessible, which means that if sigma is smaller than gamma, then the whole universe up to sigma, it's still smaller than gamma. And two, if you have a set in V gamma and a function from this set into gamma, then the sup of its range, it's strictly smaller than gamma. And finally, so large cardinal I3 was the hypothesis that there was an embedding where lambda is a limit, ordinal or cardinal. It's going to be a cardinal also. And the picture this, so you have kappa, called kappa the critical point of this J. Then everything below kappa remains the same. But kappa goes into J of kappa. J of kappa goes into J of kappa. And J squared kappa goes to J cube of kappa, and so on. And lambda is going to be the sup of these things. And so this was what I wanted to remind or recall. Now, today's what I wanted to talk about today. There are two sections. One is the relation with Laver tables, and the other is just the proof of the Laver-Steele theorem. So I was thinking we talked about the relation Laver tables. We do a break, and then we finish with the proof.
So, ~2.
A 2:15. Or okay,
Yeah, right.
Yeah.
So,
yeah. I've organized this into a modular thing where I give just the main points, say bullets, and then I explain each.
Yeah, so I prefer no break.
You for me just
Yeah.
okay.
45 minutes.
Yeah, but we can just 5 minutes for people to go to the restroom or. So, section 3, relation. Relation with Laver tables. Laver tables. So, suppose we have embeddings from a v lambda into a v lambda. And we want to define some operation that has something to do with this left distributive law. What's the first thing we can think of? Well, the composition of functions. But this is associative.
So what's J and H?
Suppose there are elementary embeddings from v lambda into v lambda. And you want to define some operation that's connected with the self-distributive law. For example, H could be just J and J. This doesn't do anything because the composition is associative. And anyway, composition is something we already know. So we wouldn't expect this to have anything magical about this. So we would, something more interesting would be J applied to H. What is the problem is that H is not in V lambda. H is in V lambda plus 1. So how can we, I'll leave this here. Well, the whole thing is that the restrictions these restrictions are elements of V lambda. So it makes sense to define this operation. So the only thing you must think is that this works as this, but for technical reasons we must consider the restrictions. And
I'm assuming that for this definition to make sense, you need lambda to be kind of large, maybe not I3 large, but right, because this union has to be again in. Am I right?
well, yeah, so lambda must be a strong limit. So in a
Yeah, something like this. So I think you know, if lambda is 5, it should more, right? Just for. But
no, it's a limit ordinal.
If it's a limit, it will always.
Yeah, because it's closed under this under this thing. So a beta.
Meaning that the I3, the lambda that comes from I3. I'm guessing that this definition might make sense even for lambda smaller than that.
Yeah, but if J, well, J must respect the fact that these are extensions of it, so these functions must cohere. So if beta is smaller than beta prime, J knows that one is a function is an extension of the other, so the images must be extensions of each other also. So there must be some elementarity involved.
Can we go
Yeah.
over this one more time? So
Yeah.
what are we trying now? We're trying to find
An operation.
some structure that
Yeah.
is left distributive
Yeah.
and non-associative.
Yes.
Okay, and you're proposing this J applied to H.
Yeah. Something that works as this. So between commas. We would like
Decomposed to H.
very much. I will show you how.
And then what was this with the restrictions?
So since we cannot apply J to H, but we can apply J to its restrictions. So I will read, I will write here something that will, for example, so if
Speaking of the thing, I just want to be
Okay, so the composite thing.
yes.
so imagine X is an element of V beta. Then J star H of X is simply J of H restricted to V beta of X.
H restricted to B.
Now notice that so H restricted to V beta by definition goes from V beta into V H of beta. This because it's an embedding. So J of H restricted to V beta goes from V J beta into V J H beta. So in particular, so J H restricted to V beta is J star H restricted to V J beta. So
Restriction is on the A, is it?
sorry.
What? What is the restriction?
Yeah. So I should.
Okay, let me see. So J star H of X. X is in V beta. And J star H of X. Like that.
Basically, this is just the definition. If you read this from right to left, this is just the definition.
No, I'm still in the first one.
Yeah.
So J star H of X is.
By definition.
So let's see. So this is a function, J star H. It's the union.
Yeah. So functions are contained are defined by their graphs.
Yes. Function is defined by this graph. Now I take the union over all beta.
All the graphs and the graphs from here.
Oh, so I take H restricted to V beta. So that's a function from V beta
To V H beta. Yeah.
The function from V beta to V. Why is it different? Oh, because beta is in lambda. So is that why? So beta
yeah.
is in lambda. So all the functions from V beta, an age of beta is in lambda. So all the functions from V beta to VH of beta are also in lambda. In particular, the restriction of H to V beta is in lambda. Good. If it's in lambda, it has an image by J. Very good. So this is a function from V beta to V h of beta, is what you've written there. And now if I apply J to it, I get a function from Vj of beta to Vj of h. Sense? And now your final equation says.
But it's just a translation, what of the definition. It's better if you read this from right to left, from like right to left. Here from left to right, and from right to left.
So if I take J star H, it's this union. Now
So they are increasing. The graphs are increasing,
the graphs are increasing here.
and you have the restrictions.
And now I restrict this Z of J beta. So the previous level, is it contained on the next level?
Yes.
It's not.
Set-theoretic.
Right, so you're saying that if, for instance, I have alpha less than beta, then H constrained to V alpha is contained in H constrained.
Yeah.
So
Because
it's
it's a
a
function,
union,
yeah.
but it's really more like a lid, right, or something, right?
Yeah.
Because all the previous sets are contained in the next one, so I'm just keeping it larger and larger. So if that's the case, then I agree that if I take this entire union and I restrict it to Vj beta, I just get the biggest element in that union that is contained in J. And that's J, and the claim is that this is J H restricted beta. And the proof is on the left, right? That's what you're saying, right?
Yeah.
Because you know, for different.
So I should. So J, I should write J of V beta is V of J beta. Probably I should have also written that. If it makes easier.
J V beta.
Because it's an elementary embedding, so it knows what are the levels of the hierarchy.
Okay, what is the statement that is preserved and implies this?
So suppose y equals v beta, meaning y is the cumulative hierarchy up to beta. Then j of y is the cumulative hierarchy up to j of beta.
Yes.
So jy is v of j of beta, so which is what's here.
So the statement y equals v of beta is a statement. You're saying that this is a first order statement in two variables y and beta.
Yeah.
So is it? What is the statement? And now simply y. What does it say?
Because the power set is definable by first order.
Yes, the power set is, but then what do you have to say? You have to.
So the elements, so v alpha plus 1 is the power set of v alpha. V alpha or v alpha prime is the union of the alphas, alpha less than alpha prime, and these are all things that you can express in set theory.
No, that's fine.
Yeah.
No, but, okay, so I'm sorry, I didn't see it. So right as a first order statement, what do I need to say y equals v beta? Where beta is an ordinal and y is some number.
You need to write a lot.
Right, a lot, but what is a lot? So beta is an ordinal, I guess.
Yeah.
First thing.
So it's transitive, its elements are transitive.
Transitive, there's and well founded.
Yeah, no, you don't need to. So that's an axiom. It's well ordered but that's a proposition.
Well, that's still first order logic, so I
Yeah.
can say it's okay. So that will imply that beta is an ordinal. Now how do I say y equals v beta?
Well, you can just say
That's set for all.
if x is an element, if it has rank smaller than beta, then x belongs to y, and b
I
and
just said they're equal sets, I just write it. No, I don't understand. Oh, I see. So you were saying, can you go back to the?
no, so suppose if x has a rank smaller than beta, then x is in y. And if x is in y, it has a rank smaller than, and having a rank smaller than alpha is something you can define also in first order logic.
So, okay, how do you define that? Just
It's
contained.
yeah. So the relation being contained. So x containing y means that for all x in x, x is in y.
That's so now I'm containment. And now you need to say for every ordinal, you say something like this, right? For every z ordinal, if z belongs to if z is contained in beta, is that it? If z is contained in beta, then z is in y. And that's an if and only if. Is that what you're saying? Sure. So you have to say a few things, right? Y is an ordinal, let's say.
No, y is not an ordinal, is a cumulative, an element of the cumulative hierarchy.
I mean, you have to say something, and I don't see how to express it in a first order logic. So what do you have to say? So you say that the rank of y, so then you need to say z is the rank of y, right? You say
there's a well, this is taking us into a whole different but it means so
but you are very certain of these things because you have the habit of thinking about them.
so the rank of x is smaller than well, you have to define the transitive closure. So you have to define x, then define the union of the elements in x, then the union of the elements in x, and the union of the elements in x, and then you do the union of all these things.
That's not first order.
It can be made into because the naturals are available. So the naturals are an element of the universe. And they are definable because they're the least inductive set. And with that, these kind of things you can define in first order logic.
I'm saying this gives you an ordinal necessarily because there's no.
No, this doesn't give you an ordinal. So this gives something which is the transitive. And from this, you get you define into some say alpha, and you can define a function such that if x is in y, then rho of x is smaller than rho of y. So this is a theorem.
First order logic.
And the rho is defined also in first order logic.
It's not obvious.
No, it's not, no, so I wanted to just, so, but, we have to move forward. So the whole thing that I wanted was just, was actually, so, so we want this.
So okay, so the claim is that there's a very complicated formula.
Yeah, that says that y is v
That
beta.
says that y is VB.
Yeah.
And it's a
So no one writes it, all, so you have to define the elements.
Okay.
No, it's like in Gödel's stuff. You don't write the whole thing because it's pages. It will be pages long.
No, sure. I'm fine with having several things. Okay, so now once you define this formula, it follows by elementariness that J of V beta equals V of J beta.
Yeah.
Right? Because if you have some y which equals V beta and you apply J to both, this has to be true. So that means that J of y equals J of V beta. No, it equals V of J beta.
Yeah.
J of y equals V. Yes, okay, so now once you have that, you conclude that this, and now what? Now you're saying that the union. You just erase it.
Yeah. Sorry.
How do you define this operation? As
No.
the union. Of beta less than union. Okay. J, basically. And now, okay, so now you claim that J of H restricted to V beta is the restriction of this thing to V of J beta. Because if I restrict this to V of J beta, what I'm restricting is this function Vj beta. So I get this level, that's the point, I don't get any level above, right? Okay. Okay, and now, so now what did you do?
Proposition. J star H is an elementary embedding. Elementary embedding. And so this is the only proof in this section that I will do. Proof. So suppose you have x in V lambda. Since this is a limit cardinal, in fact, there's going to be x is in some V gamma, with gamma smaller than lambda, because V lambda is by definition the union of the levels that are below. So, and since H is an elementary embedding, we have that for all y in V gamma, V lambda says, if you have any formula, so this comes from the fact that H is an elementary embedding. So for any y, V lambda will say this, by definition of being an elementary embedding. So not just for the y's in V gamma, it's going to say this for all lambdas, for all for any element of V lambda. But for the moment, we just concentrate on this. So another way of expressing this is V lambda says that for every y in V gamma, phi of y is equivalent to phi.
So, okay, so I start with x in V lambda. Okay, it's in some V gamma less than lambda, because lambda is the limit of the norm, right? And now you're claiming that for every other y in V gamma, it's true in V lambda that, and for any formula,
And if, yeah,
it's true in V lambda that phi of y is true if and only if phi of h of y is true. And
because so d lambda satisfies phi of y if and only if d lambda satisfies phi of h of y. Because it's an elementary embedding. And you can, and this is the same as writing this.
the first one has two things. It's not a proof, there's two sticks, I guess. It's semantic, right? It's not.
No, so by definition, this is true if and only if this is true.
No, I know, but it's just the first thing seems to only have one stick.
Sorry.
Yes, I mean, that's the claim, that J or H is elementary.
Yeah.
Is.
So, and this, I can, so now I can put V gamma inside this the quantifier, and now I cannot just say h of y because h of h is not an element of V lambda, but I can say the restriction
Of H to be. In that formula, y gamma. You can't use h there. No, but you said you can't use h because it's in.
it's too big, but I can use its restriction.
In the previous line, what's the difference?
Here, because it's just one element. So if h of y is z, so all z h of y. So if this is a generic, then I'm saying that V lambda says that phi of y is equivalent to phi of z.
Oh, okay, that's why I was sorry. So you're evaluating h of y and then putting it inside. Yes, so h is not part of the first formula. There's an h in the second. Yeah, that's not. But of course, you can't talk about the whole h because it's too big, right? So it's actually just the object that you put it. So the second formula actually has one free variable, let's say.
Exactly.
Which is
Precisely.
for h, it's the only one. Right?
Gamma. Yeah, gamma and h are the so V lambda says that for all y, so now I'm applying j. Here I applied h, now I'm applying j. For all y in v of j gamma, phi of y is equivalent to phi of j of.
Oh, amazing. So what are we proving in the end?
J star h is an elementary embedding.
Okay, so give me a second. I want to write this down. So plain here, J star H. And now just divide. So the first step is that the following is true for every y. V lambda rule is 2 lambda. So there's this formula. Let's so we're fixing
Yeah, and that's some formula.
that 5 yard, right? Now it's true, the following is true for every y, that V lambda satisfies y if only if okay, but now then of course then this implies and now, okay, now what's the next step? Oh, that's it. Yes, okay, got it. Plane, okay. The third one, yes. That implies so okay, good. That implies, and this third one uses
The J is elementary.
J is elementary. That V lambda satisfies for all y in V J by y J A equals to V n of 1. This last formula is a formula in which
No.
it's it's the same formula that's like creating.
Now, since gamma is smaller or equal than J of gamma, V gamma is contained in V of J gamma. But X was in V gamma, so X is also in V of J gamma. And so this is true of X. So V lambda says that phi of X is equivalent to phi of J H restricted to V gamma of X. But what's this? This is J star H of X. So V lambda satisfies a formula about X if and only if it satisfies the same formula about the image under J star H. And this is the proof. So this was the only proof I was going to give in this section. So we're trying to relate elementary embeddings with Laver tables. So finally, we're going to use this formula. So suppose f is some function, I'll call fk, and x is some function L. Then what's there? So I'm applying this formula, but now, in the case of f, I'll just change to another letter. In the case of x, my x is also a function. Then I get this formula.
So I'm not going to be there. So you prove, right? So it's JH is also.
Yeah, elementary embedding.
Okay, so what are you going to do now?
Now I'm relating this operation with the left distributive law. And for that, I'm going to use this that we saw last time. And what I'm saying is give different names to f and x, and you get this.
So what you're going to do is
So suppose your K and L are actually the restrictions of elementary embeddings to something. I'll not specify.
Okay, so now you find. Okay.
So what am I saying? From the definition, I'm saying that J star K star L is equal to J star K star J star L. Yeah, so I don't want to go into the indexes that should be here, but this is a proposition. And so the idea, so to prove this, you have to be more careful, but the whole idea is just this, just use this and this works. Now I'm going to erase this. I don't need it anymore. So I managed to do a close. We're going into the direction of Laver tables. We're not quite yet there. So I need it. So suppose you have J. From Laver, it's more thing. Then you can do what you can do things like this, J star J. And you can do the left powers, you can do the right powers, and combine left with right powers. And I'm just going to collect all of these things into the same object, this algebra. So the algebra of elementary embeddings of elementary embeddings generated by J by one embedding. And there's a theorem by Laver that AJ is so this is just the general culture. We're not going to use it as it is, but AJ is the free left self-distributive algebra with one generator. So if you know what are free algebras, okay. If you don't, it doesn't really matter. So basically, you can think of a free algebra is like an algebra that satisfies the least amount of equations of identities. So it only satisfies the identities that are logically provable. Or you can think of for any value that you give to the generator, it generates a map from AJ into that into another algebra.
So J is like a variable.
Yeah. Well, I could have just written as an index AJ. So I don't want to write A of n because.
So you're taking what, J and then J star J and then J star J?
Anything that you can write using star.
Finite numbers.
With a finite, yeah.
Oh,
But the algebra itself is going to be infinite.
I can just think of J as a letter.
Yes. Yeah.
Just write it down. Okay.
And this is how you construct free algebras. You just have letters and the expressions that you make from them. So, but a free algebra is going to be infinite, and we are interested in finite algebras. So, what's the relation?
You kind of need to prove that this is really free, right?
Yeah, but this is a theorem that we're not really going to use. This is just to give you the general picture.
Also, the definition is it's whatever it is generated by J with this operation star that we've defined earlier. It turns out, and this is a theorem by Laver, it proves that this is actually the free algebra.
Yeah.
So you never get the same thing. Like if you apply things in a different way, you always get different things.
Yeah.
That's
the minimum you get. It's subject to the left distributive law, so it only satisfies identities that follow from this law. It's the meaning of a free algebra.
Okay, that's not obvious, right?
No, this is a theorem.
And in this context, J is just any elementary embedding.
Yeah, from V lambda into V lambda, this is true.
From V lambda to V lambda, where lambda is the limit of.
Yeah, of the limit point of the critical points.
Okay.
But it's going always to be. Yeah, so if well, It could be lambda plus 1, but we're not looking at that. So what's the relation? Well, if you've ever heard about free algebras, then the finite algebras with one generator are quotients. So the ANs are quotients of necessarily of AJ.
Yeah, with the equation Jn equals J.
Yeah, you apply J into 1, and then you generate, and then you get all the algebra. But can we say more about these quotients? We know that they exist, but can we describe them? And guess yes. So I'm going to define an equivalence relation.
So it's something like unless n is the power of 2, the relation isn't actually equals related. There has to be something that forces me to make it.
So when I say it's quotients, they are isomorphic to quotients, obviously.
What I guess I'm saying is that I can take the algebra AJ and I can look at the equation for any n. I can look at the equation j to the power of n.
So I map J into 1, element 1, and then I have 1 star 1. So J star J is mapped into 1 star 1. And
and the question is, when is this a homomorphism of algebras? And that's only.
No, it's always. No, it's always because for a free, that's also one of the characterizations of a free algebra. It's every time you apply the generator into another algebra, it generates a morphism. It's another.
Well, then I'm not going to get a data table for some reason.
No, because.
But there's no reason 1 star 1 star.
No, but the image of a free algebra is not free.
I'm not saying it's free, but at some point you had to argue with us that n has to be a power of 2.
Yes.
But I can do this quotient for any n. For instance, 3, I take AJ and I quotient it with the relation j equals j times j times j.
But I haven't described what's the equivalence relation. So the kernel, I haven't described the kernel of the what would be the kernel of the algebra. I'm going to do this. So given J and H elementary embeddings, and given a gamma smaller than lambda limits or no, I say J is gamma equivalent to H if for every X in V gamma, J of X intersection with V gamma is equal to H of X intersection with V gamma. So this is just saying that up to the level V gamma of the hierarchy, you cannot distinguish J from H. So the definition itself is not very important. Don't think much about it. So the proposition is just that if you have J1 equal to J2,
If you just need
it doesn't matter what it is. It just there's an equivalence relation.
the gamma is less than the special point. Okay.
Yeah.
That's what you're saying.
No, I'm saying gamma is smaller than lambda.
So you seem to be saying that J and H are the same so they're the same up to gamma. That's what it's saying.
So this is an equivalence relation. So J, it's equivalent to itself. If J is equivalent to H, H is equivalent to J. all equalities, and and it's transitive because equality is transitive.
What it says. So it says that, so two, and then in their equivalent, if they are the same up to the
Gamma, yeah. If they are the same up to gamma. It's another way of saying it.
Okay, so there's this intersection which is a little bit strange, but okay.
Yeah, so this is why I didn't want to lose much time. But the whole thing is that this is not only an equivalence relation, it's a congruence relation. So J1 star K1 is also equivalent to J2 star K2. So as a corollary, you have that AJ, the quotient, this is a left distributive algebra. For any gamma, for every gamma limit.
Two, okay.
So this is the definition of a congruence relation. So it means when you quotient, this is an algebra. So
Gamma has to be a limit.
gamma must be what?
But this is only for limit gamma.
Yeah, so probably also for other, but it's probably best if we don't lose anything if we just restrict to limit, gamma limit.
Because you're going for finite things.
Yeah.
Because you're not there. It's gonna come.
Yeah, so, well, and then now you ask, okay, but I've defined some abstract thing, what does this have to do with the finite algebras? I haven't proved that this is finite. So as an observation, suppose gamma is smaller or equal than the critical point of J. Then J is actually equivalent to the identity because it hasn't moved anything. So kappa is the first element that's moved. We're only below gamma, so it's just equivalent to the identity. So this tells us that we must look at critical points to study this. So proposition. This just comes from definition. The critical point of J star K, or I'll just use H, is J of the critical point of H. Not, I think we're not going to use this, but so as a corollary, the critical point of J star J is J of the critical point of J, which is J of kappa. So you see that the critical points are becoming different. And by induction, the critical points of the right powers coincide with these ordinals. So finally, we are in conditions to say what's the relation between elementary embeddings and Laver tables. So consider all the critical points. So consider the set of the critical points of embedding generated by J. So this is a set of ordinals. So in particular, so it's well ordered. So I can order it. So there's a minimum element, there's an element after that, there's an element after that. I don't know, but there could be infinite. The order type could be infinite. So it's possible that this happens. So one thing I'm sure is that the Jn of kappas are contained in this set. So set kappa, J kappa, Jn kappa is contained in this set. So a natural question is are they equal? And after much algebra, the answer is no. Oh. And it's a consequence of this other theorem of Laver, which is, if you consider this algebra and you do the quotient with gamma, specifically the nth element in this enumeration, then this is isomorphic to an. To the Laver table.
What's preventing me from doing gamma? Oh, I see the n. The n has two to the n elements.
Yes.
Ah.
And the last powers, JP, with p between 1 and 2 to the n, are in different equivalence classes. Equivalence classes. So this involves lots of algebra, and it's quite remarkable. And so Laver was alone for many years doing just algebra.
What if I don't understand sleep? Is it?
So this is a left distributive algebra. When you do the quotient, you get a left distributive algebra, and it's isomorphic to the nth
Oh,
Laver table.
it's isomorphic to the nth-label table, and now you ask, oh, what are the elements of this?
Yeah, so it's the equivalence classes of these
I see, so the representatives in this quotient
Yeah.
are the
left powers.
left power. Sorry, coming in, left power. So the right powers give you the critical points,
They give us some critical points.
some critical points.
Left powers give us all equivalence classes.
Oh,
And corollary to the proof. So the proof is several pages. And actually, this is where Laver tables come from, because so they are a result of the study of these things, not the other way around. So one is the critical point of J to the M.
sorry, so late studying large cardinals and you came to
Yes.
this table, it's not
Yeah.
you were studying these tables and eventually found the
And
large
large
cardinals
cardinals.
different way.
It would be very weird if this had happened.
Yes.
So the critical point of this is the nth. The critical point of any JP is gamma L, where 2 to the L.
Sorry, I need some help.
Yeah.
I'm trying to copy that, so the gamma 0 is K, gamma 1 is J, K, so on, right?
Yeah. So actually, what's going to happen? So gamma 0. Okay.
Is gamma 0, gamma 1 the ordering of grid or is it?
Of grid, yeah. So gamma 0 is kappa, yes. Gamma 1 is J of kappa. Gamma 2 is J square of kappa. But gamma 3 is smaller. And this is actually gamma 4. And the reason I'm going to write it right in this board is that, but I'll first say, so the critical point of this is the L, so 2 to the L is the greatest power of two that divides P. So if P is odd, then its critical point is kappa.
Oh, the supremum is the same. Oh, that's a question actually.
No, the supremum is lambda, yes.
They interlace, right?
Yeah.
These two lists.
This is it.
Sorry?
What is this? So,
I was waiting for.
but there are two economics. That's
Yes, so I'm going to. So in general, this happens if and only if the period of the pth row is 2 to the m in an and 2 to the m plus 1 in an plus 1. So there's a character. So
So is there any sense? I take GP and I apply it to nth critical. That equals the nth critical point, if and only if. I look at the pth row
in an,
in AN, and that period is 2 to the n. Period is 2 to the n. In AN, and it's 2 to the n plus 1. In AN plus 1. Okay.
so this is just
So if you look, so that's if this n is one of these points where which are very few, very sparse, where the period increases.
yes, exactly.
So what you're saying is that if you show that the image of this JP, well, you want actually J1.
For the first row, we are just looking at the images of J.
There's J. So if you show that the images of J of these critical points are unbounded, right?
Well, I have to show that between any of these two elements, there's just a finite number of gammas. So to show that the periods go to infinity.
In these two elements, there's a finite number of gammas. Why is that enough there?
So this is the next section, the Laver-Steele theorem, but I think we can go through if we're going to break. I think it makes sense. So we have these gammas, and it could be that there, for example, there's an infinite number. Suppose that there was an infinite number in some interval. Then take the first n such that there are infinitely many infinitely many gammas here. So this would be some gamma m0. And then when you compute J gamma m0, this would be equal to some, if it was infinite, this would be equal to some gamma alpha, and alpha would be bigger than all L in the naturals, right? If there was an infinite number of gammas here. But then, if you look at the first row of the Laver tables, they would never go from 2 to the m. The period would never change from 2 to the m to 2 to the m0 plus 1. If there were an infinite number of gammas.
Oh, I see. So you're saying, I see, but if there aren't, that's your point. So suppose there aren't an infinite number of gammas.
Yeah, we want to prove, that's what we want to prove, that there's only finitely many gammas, critical points in an interval of this kind.
So you're saying if that's true, and I start with J, so I see what I get, and I start with gamma 0. I get, what am I gonna get? The claim is that.
So my claim is proving that the periods tend to infinity is the same thing as proving that there are just finitely many gammas in each of these intervals.
You also, another way to state it is there are infinitely many gamma I, with I being a natural number in the sequence of J of.
Well, that's already true because this is contained. So, yeah, I get it. Yes, no, yes, it's what you're saying. Yes. So J3 of kappa is gamma 4. J4 of kappa is something huge, but it's finite. But this is finite. This is what we want to prove.
Want to prove that for an infinite sense.
So, how do we, in set theory, or so we have this abstract set, and we want to prove that it's finite. How do we go about doing this in set theory? Well, we go by contradiction. We suppose it's infinite, and we prove that something that shouldn't be happening is happening. In this case, what was the property of ordinals that I mentioned was the most important? There's no infinite decreasing sequence of ordinals. So I want to prove that if there were infinitely many gammas critical points here, then there would be an infinite descending sequence of ordinals. And what are the ordinals? There will be order types of things related to these embeddings. So I don't know if you want to make the break here or. Yeah, I'm relaxed because we're not going. I'm going to give the main details, but not the most technical proof.
It's alpha knowledge.
Yes, alpha. Yeah.
Is that enough?
Yeah.
Should we take a
So
break?
5 minutes, yeah. Laver-Steele theorem. Laver-Steele theorem. Which is that the periods of Laver tables tend to infinity. So it's like I said, we're going to prove that if there were infinitely many critical points below any of these Jn of kappa, then there will be an infinite decreasing sequence. So now, now I'm going to give you a definition that you need to be a set theorist to think of this, and specifically a set theorist that does inner model theory of large cardinals. So, but it had to be one of a very restricted set of people. So it wouldn't be me, for example, that would have thought about this.
What are you going to do?
I'm going to define a set of ordinals. So I'm going to start with an embedding, and the gamma smaller than lambda. Then my set of ordinals will be like this: L applied to F applied to X, where F and X belong to V gamma. X obviously is in the domain of L of F, and F takes values in the ordinals. L is just an embedding. So for each embedding and each limit ordinal gamma, I define this set. So there's a terminology which I don't know if it's useful. Terminology. But I'll just say it. So the elements of S L gamma are said to be gamma representable by L. So this terminology, I don't know if it helps or not, but I'll just say it anyway.
Fx in V gamma, such that for every x, f of x is an ordinal, right? And x is in the domain. Wait, yeah. In this set, x is in the domain, so it's the images of L vector for every function from the output. Okay.
Don't think too much on this.
There's no point. So what you're saying, it's trying to say. Okay. Okay, so it's the set of images of functions.
So for now, it's just the set defined with this formula. So
This is also a set of points.
yes, it's going to be, because if F takes values in the ordinals, L of F will also take values in the ordinals. So the first observation is that the definition only involves elements of V gamma. So these two sets of ordinals are the same. Just the second observation is if you have two ordinals and one is smaller or equal than the other, then SL delta is contained in SL gamma. And this is because V delta is contained in V gamma. Third observation is suppose you have an ordinal in V gamma. You can consider the following function.
Mapping 0 to.
Yeah, so it has just one element in the domain, and so f of 0 is beta. This is the same way of saying. Then what is L of f? So this is the same as saying f of 0 equals beta. And L of f is this L of 0, L of beta by elementarity. But this is just 0 because an elementary embedding doesn't move finite stuff. And so LF of 0 is L beta. So the image of gamma under L is contained in the set of ordinals. So this is the main thing we're going to use. But as a remark also, we're not going to use this, but suppose F is the identity restricted to some ordinal beta plus 1. Then L of F is going to be the identity restricted to L of beta plus 1. And so in this case, LF, since it's the identity, it's just beta. So we also have that gamma is contained as L gamma. But I'm not going to use this. The other is the important one. So, and now finally, well, theorem. So this is due to Steele, but the itself this is distilled. Distilled as by Dougherty. So the original proof was a bit complicated. And Dougherty gave this this one with this more simplified set. Is the following: assume you have the following situation: an embedding J2, which is formed from two other embeddings. And suppose the critical point of J1 is smaller than some gamma, and gamma is inaccessible. Inaccessible. Then the order type of S J1 gamma is strictly bigger than the order type of S J2 gamma. And so this gives us the Laver-Steele theorem. Why? Suppose, for example, gamma is some j n plus 1 kappa. We know, and consider the left powers. If all these critical points were below this gamma,
This L.
sorry,
L is any non-trivial.
yeah, no, it might be trivial. Yes, it might be trivial.
If it's trivial, then.
Yes. So if L is the identity, then this is all the identity, and J is also the identity. So yeah, so it doesn't make
It has to be non.
no, then it's trivial because then this is just gamma. So no, it would also, well, assume they are not trivial, but it's
No, it's strictly trivial, right? Those cannot be the same.
so if L is trivial, then J2 is also is trivial. So this is just gamma, and this is easy to prove.
But then J1 is not equal to J2 is. Oh, L is okay. L is trivial, J2 is trivial, but J1.
It's not trivial, yeah. And it's not because we're saying that the critical point is already. So consider this situation. If all critical points of the JPs were below gamma, then you would have the situation, the order type of Sj gamma would be bigger than the order type of Sj2 gamma should be equal than the order type of Sj3 gamma, and so forth. And this is impossible.
JP or below.
So suppose you add some gamma, well, this is just to be inaccessible.
So what's the, what are you saying? So I take gamma to be j to the n plus one of.
Yeah. So suppose gamma is inaccessible.
But isn't it, that's not being whispered, so.
Yes. No, so, yeah. So here, I'm not saying that gamma needs to be a critical point of anything. I'm just saying if gamma is inaccessible, then this theorem is true.
But you've proved at some point that all critical points are inaccessible.
Yes.
So it isn't.
Yeah. This is a particular case of an inaccessible gamma.
Very good. And now. J equals one, that's the definition, right?
Yeah.
So if all critical points of JP were below gamma.
The JPs. Yeah.
So what's the order type of J gamma? That's.
I should put here J is J1.
Your JPS is just numbers,
Yeah. P's, P being dimensions. Yes.
These are fixed now, right?
No, I'm varying. So I'm, here I apply P equals 1. Say J1, say, for example, in the first situation, J1 equals J, L equals J, and J2 equals J2, J index 2. Apply the theorem, and you get that the order type of SJ gamma is strictly bigger than this order type. Now apply the theorem with J2 in the role of J1, J in the role of L, and J3 in the role of J2.
But these are cardinals, so that can happen. Right?
Yeah, so it cannot happen that you have an infinite decreasing sequence. So what's wrong? Well, what's wrong is that we assume that all the critical points were below gamma.
Yeah.
So there must be some critical points above. Yeah.
Above gamma. Yes.
That's all we need. So there must be some gamma m that's bigger or equal than that gamma. I put +1, yeah. So m a natural number.
Oh, yeah, okay.
So yeah, so remember the critical points of the JPs were of the form gamma L, where 2 to the L divided P.
Oh, wait, so wait, give me a second. So you're saying because. So you're saying because all these critical points of all this algebra, they're well ordered. And there's and there's natural and natural numbers many. So I can just order gamma 0, gamma. Is that right? Okay.
Yeah, so we have a subset of all the critical points, but we are actually proving that they cover all critical points.
Oh. There's an accountable number of critical points, but nothing tells you that this order type is like 1, 2, 3, 4, 5. I mean, it could be anything.
yeah.
Right? There could be limits, there could be.
Yes.
Right? And now what you're saying is, let's look at this subset, namely the critical points, I guess. Oh, JP. JP. Oh, you want to prove that there's no limit? That's what you want.
Yeah.
That's all you
Yeah.
want. So you're supposing there is. Oh, they're all below gamma. That gives me this infinite descending chain. That's a contradiction.
Yeah.
So so if I look at all the critical points of these JPs,
They're of this form, the gamma L, where 2 to the L divides P. So this is, for example, a critical point of J to the L. There's going to be, there's one where this happens.
So this I understand proof. So if you want to prove that there's only finitely many gammas between each G. If this isn't the case, then there has to be some kind of limit ordinal between J and P and J plus 1 or something.
Yeah.
Right? That implies that I don't understand why the negation of this, what's the negation of this statement? Right?
So
There is no gamma, right? There's no gamma,
yeah,
which fits.
which has infinitely many critical points below it.
Just infinitely. Oh, infinitely many. Just infinitely many of these critical points of the GC. But why couldn't there still be a gamma that only has finitely many critical points of the JPs below it, but infinitely many gamma i's? You see what I'm saying?
because that's what it cannot happen.
No, that's because of the station.
Because these are all so the these are all the gamma m's. If you consider the left powers to the m, you get all of these.
As you go over JP's the dimensional number, you go over dimension.
You go from all gamma m's for gamma.
So consider the left powers. The critical point of J is kappa. The critical point of J2 is gamma 1. The critical point of J3 is again kappa. The critical point of J4 is gamma 2. And so they're going to repeat. So, for example, if P is odd, then its critical point is gamma 0. So you're going to repeat, then go up, then go down. It doesn't matter. It's always one of these, or one of the first gamma L's. Yeah. And it's 415.
Yeah, I can actually leave in 10 minutes, but I want to make sure we finished everything. Yeah, so sorry, I just got lost there. Let me try and just begin. As I recall, you wanted to prove that for some p, right, I start with JP of so I start with JP and I apply it to gamma n. And this big theorem by Laver shows that this will tell you the point where the period goes from 2 to the m to 2 to the m.
Yeah. But I don't need that characterization. I'm just looking at the critical points for the moment.
Oh, you're not finished. Prove it.
Well, well, I wanted to prove this.
Let's take that as a axiom.
Uh,
Oh, you need to prove it.
well, I wanted to give the main points. Yeah.
But I'm trying even just understanding this theorem, I'm trying to understand how the proof falls, right?
So you understand how to apply this from here to here.
I can read the words and see that, yes, so it should follow that. Again, it's J to the end. Oh. Okay. Ah. So gamma is J to the n plus one. I think that's the point. So okay. I see. So take gamma to be J to the n plus one. Let's prove that there's no infinite number of gamma i's before that.
Yeah.
Okay. Now, take your P, your element P. Let's prove that there has to exist a P such that it maps the gamma m below gamma into some gamma m above gamma. Is that it?
No, you just need to that the critical point is bigger than it's going to be bigger than gamma.
Sorry, the critical point, yeah, that's okay. So JP of gamma n equals some gamma n, right?
So in the row, the period would change from 1 to 2.
No, I have one specific example.
Yeah. Okay.
Sorry.
So the critical points of the JPs are gamma L's. So L's in the naturals.
Yes.
If all the gamma L's were below gamma, you get a contradiction, right?
Yes.
So there must be a gamma L that's eventually bigger than gamma. And all the other gamma L prime with that are bigger or above because they are ordered.
So you start by defining the set of critical points.
Yeah.
Right? Actually, that means, okay. So you started by defining the set of critical points.
Mm-hmm.
Right, so this is a set of ordinals.
Yeah.
And there's a natural
Ordering.
there's a natural number of many of them.
Yeah.
And now you plan, this is a well-ordered set,
Yeah. It's always because it's a set of ordinals.
because it's a set of ordinals. Now, the only issue, might suppose that it's like 0, 1, 2, 3, 4.
So it could be
Then
that.
there's no issue, right? Then there's no issue.
Yeah. So if the order type, if the order type of the critical points was omega, which it is, there's no problem.
There's no problem, exactly.
But it could be, say, omega square or something like this.
This would be a problem, right?
Yeah.
Because then there would be like infinite number of these things.
Yeah.
So you want to prove that it's omega and not omega squared.
So which is the same as proving that below any
Exactly.
of these, there's just finitely many.
Right, actually, you don't even need to prove that it's omega, because maybe the whole thing is omega squared, but you just want to prove that on the interval that contains all the j to the n's, there it's omega. Right, if you've proven that.
No, they're finite.
No, but I take the union of all j. If I take the
Yeah.
union, the intersection with this is omega. So there's no infinite accumulation.
Yeah.
It could be further ahead, maybe. So I just want to prove that, right? Okay. So for this. For this, you're going to look at this set of elements in your algebra, right, whose critical points are all finite. They're all gamma 0, is that right?
Yeah. Well, I have a finite index.
Gamma finite. I prove that there's always one which is bigger in this finite, in this omega set, there's always one that's bigger. Any j, right? Fix any j n plus one, there's always one that's bigger than it. And the fact that it's finite, it's this statement one. That it's this.
Yeah, well, yeah, so I should say for all the M belonging to the naturals, gamma M is the critical point of J to M. So what's more important is the corollary two, not the corollary. It says that, so I have a description of what these JPs are. They are the gamma Ls. And what I'm saying is that it cannot be that all the gamma Ls are below gamma. Because then you have an infinite descending sequence, which is a contradiction. It's 425. I think I can write this and then I'll scan it and I'll send you.
Okay, yeah, if you could scan your.
And just record to you. So.
I believe in it.
Thank you.
So thank you for coming. This has been